Right, so you go from gray code to decimal to binary in your head, basically. There's no
you change one bit at a time. So that's how you remember it. And so
I get that, but okay, that's it.
yeah, I don't know this by heart. I have to look it up. I hope he doesn't expect us to know this on this round.
So let's start. So first I'm going to go over several key points that were in the lecture, but I'm going to show them in problems, like see how they are used to solve all these problems we see in homeworks and quizzes. These problems are going to be similar, some of the just taken from the homework, but they're sort of different. So first is the signal transformation thing. So this is not about any problem we saw, but I just want to make sure you guys understand this part. So when we're talking about signal transformation, it's like first we have one original signal, and then we have something looks similar to that. Yeah, that is another signal. Maybe we add a scalar or.
Are you writing?
Yeah, I'm writing. Oh. Let me see what is happening. Stop. I don't like this. Let me try to do this again. 6, 5, 6. I can see that. Okay. So, well, one signal is the original signal. Then we have something similar to that. Yeah, we know the shape of the original signal. We know how it looks like. Then we want to know how the new signal looks like. So there are several transformations.
I was thinking also take attendance and you can give them credit to give them like office hours credit. Like,
okay, so
you can pass it on a sheet. And
okay. So I don't have a sheet right now, but we can do it later. Okay, we can do it later. So first is time shift. So I can see that this is one kind of time shift. Also, we can have plus tau, and it is important to remember the direction. And usually, I see that it's left plus, right minus. Is that t minus tau go to the right, and t plus tau go to the left. So whenever you cannot follow me, just ask me a question. Stop me. Okay. So, and scaling is like there is one factor before the signal. And this factor can be negative, so it can be minus xt. So that is actually flipping the signal with respect to x-axis. And then we have time reverse, which is have a minus sign before t. So when we're talking about time reverse, it actually is doing the mirroring with respect to y-axis. So always keep in mind y-axis is evolved in this process. So also scaling actually is one special case of time reverse is actually one special case of time scaling. Time scaling is like xat. So when a equal to -1, this is time reverse. And when a is larger, that means the signal is actually became shorter. So for example, if xt looks like this, and x2t will look like half the width of it, like this one, and the center is always y-axis. Okay, so the last thing I want to say is the sum and product of two signals. You are going to use that in convolution a lot. So it's like you have two signals. Like this one is one signal, and there is another signal. You want to add them together. Question?
Could you show an example of a time scale that's not centered about the y-axis?
Sorry, time scale is always centered about y-axis.
Oh.
That's the point.
Okay.
Yeah. Yeah. So, well, let's see. Let's do the sum of these two signals. It's like when you want to do the sum, it's actually you take one point and sum this 2 points. It's like this length sum. Can you see the cursor? Mm-hmm. Okay. It's like actually doing the sum at this t and do this kind of operation over all t's. So for this one, you actually got some square wave like this. For the product, you're going to do the same thing, but usually when we do product, it's like we want to find the common non-zero range of the two signals, because anything multiplies 0 is 0. So when two signals doing product, first you want to find the common non-zero area of these two signals. Okay, so maybe I'll ask a small question, like, so for x 2 minus t, so is this one shift to, well, let's say how you can get x t to x2 minus t.
So you do a time scaling. You
Flip, time reverse.
Yeah, it's like a time scale, but then it's a special case of time scale where you did a -1 and then time shift.
Time shift to which direction? That's the
plus
force.
2, so that it's to the left.
Okay, let's do what you said. So first we do x minus t, which is flip, and then second thing is we do plus 2 is shift to the left. So that is x minus. So when you do this kind of operation, it's like you do inside t itself. So here it is a t. So here it will going to be shift to t plus 2. That is shift this second signal to the left. So actually this one becomes x minus t minus 2. It's not the right direction. So what is this one? You can see that, well, it can be x minus t and then shift to the right, minus 2, and this will become x2 minus t. Or you can see first shift it to the left by 2 and then flip it. These are the two ways you get this signal. Yeah. So then let's come to the real problems we see in quiz and homeworks. So first thing I want to talk is the system properties. There are 5 properties we care a lot, and I want to group them into 3 based on how you solve the problem. It's like when we see a property, it's like a system can have a property, or it can happen a system does not have this property. So the problem often asked is, does the system have such a property? So when we want to prove a system have the property, actually there are conditions linked to each property. It's like there are conditions for memoryless or condition for linearity. So what we usually do is we do this structure. So we say if the system satisfies one condition, then we say the system has the property. If not, it does not have. So there are 2 ways to do this if statement. And one way is we can do math proof. It's like we calculate something about the system, and at the end we see something that is the same as the condition or contradict to the condition. Then we can conclude it satisfy or not satisfy. But there is another shortcut, is the counterexample. It's like if the system does not satisfy this condition, you can use a counterexample to say, well, this is where the system does not satisfy, then it does not satisfy, then it does not have the property. But the problem is, you can only prove does not satisfy with counterexample. You cannot prove the other way. So we will see for some of the property, we want to first try to find out the counterexample. If we fail to find it, we have to go back to the math part. So the first group of the property is memoryless and causality. So these two properties are related to the history and the future. So the condition. So these are the property, and below are the condition. There's two ways you can use either of them. So the condition for memoryless is the current output does not need nothing but the current input. Or we can say the other way, the current input does not need history or future input or output. Sometimes you can say output. And causality is a little bit broader. They say the current output does not, the current output need only current input or output or past input or output. And the other way of saying that is the current input does not need future input or output. So it is recommended that you try to find a counterexample for this kind of properties, and if not, then we go to the math. Question?
If a system is memoryless, is it automatically causal?
Yeah, actually memoryless is one special case of causal. Yeah. So there are two examples. One is discrete and one is continuous. Actually, almost exactly the same. The only difference is n and t. So the first thing, let's talk about like memoryless. So I want to try to find one counterexample, but it's not that obvious. But it shows me this expression is very similar to the definition, the condition, right? So we can just use the condition. Yeah. So what is this part? So what is n? Well, sorry, it's a bad question.
Scale, depending on time.
Yeah, it depends on time, but it's like time is always seen as given. So n is just a given, so it's just a number. So and cosine is just a piece of math operation, so it does not related to the times. And then the only thing left is x n, and this is the current input. So we can see this system, when we want to acquire y and the current output, the only thing we need is the current input. This is exactly the same as the condition says. So we see this is memoryless, and as you have just said, so if the system is memoryless, then it is automatically causal. So the first example is memoryless and causal, and the second thing, well, let's try to find one counterexample of that. So can anyone find one counterexample saying this is not memoryless?
If you plug in t as 1, then it requires input from time 1/3 or something.
Okay, good. y1 requires x 1/3, and 1/3 is less than 1. That means it is asking information from the past input. So anyone can give a counterexample saying this is not causal.
If t is equal to minus something.
Yeah, sure. So if t is equal to, let's say, -1, then it requires the input of -1/3, so it's actually requiring information from the future. So these two are very good counterexample, and that's enough to say it is not memoryless, not causal. So then we go to this group of property. So the proof of this property is going to be a little long, but if you follow the step, it's going to be easy. So for this two property, math proof is highly recommended because counterexample is not very easy to show these two properties clear. And the conditions of these two properties is something like the output is not going to be changed if two operations are swapped. So let's go to the time invariant property first because it's easier to explain. So it's like the output will not change if the order of the system that we want to talk about and time shift operation, these two operations are swapped. So when we want to illustrate how this works, it's like when we want to prove a system satisfy this condition, actually we want to create two signals and then compare, are these two output the same? If the same, then it satisfies. If not, then it does not satisfy. So the first thing we can see, let's let the input signal go through the system first, then shift. So the original input is xt, and when it goes into the system, then we are going to have the original output yt. So this block diagram, I don't know if you are familiar with this. Block means any kind of operation, and arrows means the signal. And then let's put this yt into a time shift, like plus tau, and then we are going to have yt plus tau. This is the first output. And then we create another signal by first time shift that, and then use the shifted input go in through the system we want to examine. So it's xt, that's plus tau first, and then we are going to have xt plus tau, and then go through the system. And finally, we are going to have fxt plus tau. Well, if these two signals yt plus tau is the same as fxt plus tau, then it is time invariant. If not, it is not. So it is a little bit confusing sometimes when we are doing problems like what's the difference from y and what's the difference from fx. So let's do one example to see what's the difference. So for the first problem, can you see that? I think it's a little bit small. Can you see that in the back? Okay. So let's create the first signal, that is the delayed output. So yt plus tau for the exponential one, for this one, is exponential xt plus tau. So for yt plus tau part, it's like in the original function, whenever you see a t, change that into t plus tau. It's like t change into t plus tau. Well, this is not math, don't copy this part. I just want to take a note of that. So don't take note of this. So then we want to do another thing is fxt plus tau. And this is whenever you see an x something inside, let's say x star, you change that into x star plus tau. So I see one xt here. So for the first problem, star is just a t. So here I put exponential xt plus tau. So I get the second output. And then I will see, well, the first line, the output of the first line, the first signal is equal to the second signal. Well, in the solution, I will write st plus tau equal to fxt plus tau. So thus time invariant. Well, let's do another problem. So yn equal to x minus n. Let's do this one. So I still use tau for the delay. That's easier. N plus tau equal to, whenever you see an n, that you change n into n plus tau. So I have x minus, then this n is changed into n plus tau, but inside the parentheses. So this n plus tau. And then the second signal is like fxt plus tau. So whenever we see x something, we change change that into x something plus tau. So here that the something is minus n. So that will give us x minus n plus tau. So we can conclude that yn plus tau does not equal to fxt plus tau. So this one is not time invariant. So for question.
So in the y of n plus tau, that's where the output of the system is shifted afterwards?
Yeah.
Okay, and then the second one is the input is shifted
and
then put in the system.
So this is time invariant. Another very similar one is, what happened to this? A very similar thing is linear property. So when we're talking about linear, we're actually talking about linear combination. So any of you don't know what linear combination is? Okay, so assume you all know what linear combination is. So a very simple example of linear combination is if we have two input, we add some scalar before that. So a x1t plus b x2t. This is one linear combination of two input signal. So what we are comparing this time is the first is we want to put this signal inside the system first, two signals. Then we got y1t, and also we have x2t put into the system, and y2t. And then we do the linear combination. Then we are going to have a scalar times y1t plus a scalar times y2t. This is first go through the system and then do linear combination. But we can do another way, like first do the linear combination and then go through the system. This will give us x1t plus b x2t, and then go through the system. Then we are going to have a x1t plus b x2t. So if these two outputs are the same, then we can conclude the system is linear. So let's go to one problem. Well, still these two problems, but we try to solve linearity for these two problems.
Can you go back to one day?
Actually, I'm going to share this video.
Oh, okay.
I'm recording this video for you, so you can go back to it online.
Alright.
Okay. Yeah, and also everything here, the notes and the problems, I'm going to share them.
Okay.
So first is yt exponential xt. So let's create y1t and y2t, and y1t is exponential x1t, and y2t is exponential x2t. So then let's do f a x1t plus b x2t. So what is this one? So here it is very clear that f is just the exponential. So we have the third output xt is exponential this thing. So it is clear that okay, let's just write things completely. So the linear combination of x1 and x2 is a y1t plus b y2t. That is a exponential x1t plus b exponential x2t. And this one does not equal to y3. So because for exponential, you cannot just split that. So we can conclude that this one is not linear. Well, this one is sort of clear because we can easily tell what the system is, what fx is. But for most of the problem, it is not that clear. So let's see the other example, yn equal to x minus n. So y1n equal to x1 n minus, sorry, y2n equal to x2 minus n. So y3, let's first still write that as f and the linear combination of the input a x1n plus b x2n. But the system is described as yn equal to xn. It's not x minus n, but it's not very clear what f is. So we're still going to do the star trick. So it's like here, well, whenever we see an x something inside, let's say x star, we change that into a x1 star plus b x2 star. Well, here star is minus n. So this y3n will equal to x1 and star is minus n plus b x2 minus n. And we can see that ay1n plus by2n is just ax1 minus n plus bx2 minus n. So this one equal to y3. Because it equal to y3, we can conclude that this system is linear. Question?
For the first y3, should that be f of ax1 of negative n? Or
First y
yes, that.
here. You mean f inside f?
Yeah, shouldn't it be negative n?
Here. No, because this is the definition. So xn is the input. So ax1n and bx2n is the linear combination of two inputs.
Okay.
And this replacement is also according to the definition.
Okay.
But what's different from each problem is what the star is. Question?
Can you give an example with a different function, like y of n equals x of 2 minus n?
Can I say that again? Y of n equal to 2 x
X of n of 2 minus n.
Can I say that yn equal to
X of n
x of n
minus 2.
minus 2? Just minus 2? Okay.
Wait, no, the 2 is in the.
Okay. Inside. So the problem changed into yn equal to x n minus 2. So y1n is x1 n minus 2, and y2n is x2 n minus 2. And this line will not change because it's the definition. This line will not change, and star is n minus 2. And y3n is we plug the star in, so this one is n minus 2, and this one is also n minus 2. And ay1n and by2n, we just copy this first two lines. So this ax1 n minus 2, this is copying the first line, and bx2 n minus 2 copying the second line. And let's say if y3 equal to this thing, so we see, well, they are the same, so still the conclusion is this system is linear. Okay. So let's go to the next property. The next property is like not very official definition, because we're going to talk about stability later when we come to the Laplace transformation. But here we just see bounded input and bounded output stability. So here also we try to find the counterexample first, and if we cannot find, we are going to go to the math proof. And the condition is for whatever a bounded input, the output will also be bounded. So to find one counterexample is like, well, I can find one bounded input that gives this system an unbounded output. This will tell the system is not BIBO stable. So So the example of this, this first one, yt equal to dx dt. So we can find one counterexample to see that this one is not bounded input, bounded output.
Square wave.
Yeah, you can have a square wave. What happened to this? So for a square wave, you can have this part, you have infinite derivative, and this part you also have an infinite derivative. So by this counterexample, you can tell the derivative system is not bounded input, bounded output stable. So for the second example, so can anyone find one counterexample for that? No. So it looks like not very clear what counterexample can be. So we're going through a math derivation of this. So we have to go through this. So for the math proof, the first step is saying I have a bounded input, but it's an arbitrary function. That means whatever xt, as long as it is bounded, I take it. So I give a number for the bound, let's say bx, and then I try to find what is the bound. What is the magnitude of yn? If this one is bounded, then this one is bounded input and bounded output. But if this one go to infinite, then it is not. So let's copy what's inside here. So let's put this thing, everything is in the absolute value. X minus n minus x n minus 2. So even though here is minus sign here, but for the absolute value, we still add them together. So it is, this is not equal to, it is like this number by what is called triangle whatever. I forgot the name of that, but triangle property. Well, I forgot the name. It's like, well, this one have to be smaller than the sum of the absolute values. Well, for the first part, for this first part is like the original signal time reverse. But time reverse does not change the magnitude. So the first part is still bx, and the second part is time shift. And time shift does not change the magnitude. So this part is also bx. So the answer is 2bx. Remember, this is the bound of yn. Because yn, the absolute value of yn is always less than 2bx, then we see this system is bounded in and bounded up. BIBO stable. Okay. That's for the properties. Then let's go to another topic. So this is not a problem, but this is something that I think you guys should know. The first thing is the delta function, and then, well, I should say it is the unit impulse function, and the second is called the unit step function, and the third one is called the unit ramp function. So the shape, you can remember them by the look. So if there's a discrete signal, then the unit impulse function is only non-zero at n equal to 0, and the value is 1. And the unit step function looks like this, and everything after that is 1, is from 0, and after that it is always 1. And the ramp function, maybe you're not going to see that, but ramp function is from 0 you get Rn equal to n. So it's 0, 1, 2, and so on. So this one, maybe you are going to see that when you see Laplace transformation, but for this two, currently you are going to use that. Usually, we are going to use the step function to see one non-zero range. It's like if I have a function fn, sorry, I have a signal fn, and if I times that by a step function, that means I want to cut some part of that signal to be 0. And usually this un can be shifted, like +2, or sometimes it is reversed, like -n. So, but you always know what is the non-zero area of this u something. But for this unit impulse function, actually we're going to talk about some property of this impulse function. So first, the two properties that is very easy to understand. Well, I will not talk about understand part. It's very easy to remember and use. The first thing is if you do convolution with one signal and a delta function, you get the signal itself. If you do convolution with one signal and a shifted delta function, you will get a shifted signal. That's what the first two lines say. And the third line, you're going to see that in homework 3 is when you have a delta function inside the integral. How we use that is we see this delta function is shifted, right? And because delta function we see, well, it is at 0, right? So if a delta t minus tau, that means this impulse is at time tau, right? So that is the position of the delta. So here the position of this delta is tau, and we want to know if this position is inside the range of the integral. So if this tau is inside this range, like bigger than a or less than b, then this integral automatically become the evaluation of the function at that position is f tau. But if it does not, if tau is not inside that range, the integral is just 0. So let's do two examples of that. So first one, this is just the delta t. That is just the delta t minus 0, so the position is just 0. And we know that 0 is definitely greater than minus infinite and less than infinite. So 0 is inside the range. Then where is ft here? And here ft is whatever is multiplied with delta t is this cosine t. So the integral will finally equal to this function at 0. So that is cosine 0, which is 1. For the second problem, this is delta t plus 3. And delta t plus 3 is delta t minus 3. So the position is minus 3. Question?
Yeah, for the first one, right?
Mm-hmm.
So the delta t would make it just 1 point at 0.
Yeah.
So how can the area under a curve of 1 point equal to 1? Wouldn't that be the cosine?
Yeah, I forgot to explain the definition in the continuous area. So for this is the discrete area, right? But for continuous, well, if this is n, if this is t, delta is not 1 at 0. It's actually delta is infinite at 0. But even though the magnitude is infinite, its integral is not infinite. So that is how delta function is defined. Sounds a little bit weird, but this is how it's defined. So delta t is infinite when t equals 0, 0 otherwise, but the integral from minus the infinite to infinite equal to 1. Yeah, equal to 1, just delta, sorry, this should be delta t dt. Delta t dt equal to 1. This is how it is defined, because you see the second property of delta function. Then when you do the integral here, it is not going to give you a very small value.
Hey, I'm a little confused. If cosine t times delta t is just cosine of 0, right? And then
Yeah.
you're taking the integral from negative infinity to infinity with respect to t.
Yeah.
That'd be like 2 infinity.
Well, let's say let me try to answer your question first, and not very strict math. So delta t is just non-zero at t, right? So we can write this minus infinite to infinite to be minus to be just left to the 0, which is 0 minus t, to 0 plus, just the left to the 0 and just the right to the 0, right? And cosine t delta t. So for this one, it is infinite, and this one is because this one has a finite number inside the range, and range is super tiny. It's called infinite. So this one actually has a limit to t to 0, right? The integral of this cosine t from
The integral from anything from 0 to 0.
yeah, it's almost a 0.
Yeah.
So
Okay.
so but this one is going to infinite. So these two, if I cancel, then you have a finite number here. Well, it's just a very intuitive, yeah. Okay. Well, did we talk about second one? Okay, so let's continue. So delta t minus 3. For this part, the position is minus 3. But the range is from 0 to 5. So minus 3 is not inside the range. So this one just equal to 0. Question?
So you take the convolution between these. You're not just multiplying, right? Because there's no simple convolution.
Just multiply.
This is just multiplying them?
Yeah, inside these two examples, there's no convolution.
Oh.
Yeah, whenever we write convolution, we will use star or fancy stars, but not ignore it. We have to have the star there. Well, for the other property about the convolution, we're going to talk about that in the convolution part. So, impulse response. So, we have already talked about impulse signal. So, what is impulse response? So, when we talk about response, it is like the output of the system, something about the output of the system, not exactly out signal, but here impulse response is the output signal of the system if the input signal is an impulse signal. So we're going to see that in convolution later, but currently we just know that when a problem gives you, well, this is the impulse response, the thing you know is that there is an input signal and that is the impulse signal. So for in homework 2 and 3, there are problems like, well, if this is the impulse response, is it causal and is it stable? So this is what we want to find is the relationship between the output and the input, and the input is known as impulse response. It's impulse signal. So let's first talk about the causal part. So for Hn equal to this one, and this is the output, and the input is like an impulse signal. It's like it only non-zero at 0. That means the input, or I should say there is no input before 0. Only when n equal to 0 there is an input. So when a system is causal, that means there is only output when there is input. So we see before 0 there is no input. So if the system is causal, that means there should not be any output before 0. So
-2 in this case. -2 in this case as it shifted to the left.
Negative shift to right. Oh, negative 2?
The zero's at -2. That's the...
Yeah, +2, that it starts at -2 and then it's 7.
Oh, let's see. Yeah. Okay. So ut, let's say the first output. So this part is always non-zero. So let's just forget this part because it's always non-zero. Then we try to find the non-zero area of this un plus 2. So un is like from 0 and un plus 2, and plus 2 is shifted to the right. So un start from 0 and un plus 2 should start from 2. Well, let's check about that. So if oh, sorry. Oh, sorry. As the plus is left. Sorry. This should be negativity. All right. Plus is shift to the left. Sorry. In the first slide. Remember that. Yeah, I confused myself. Sorry about it. So it starts from -2. So as we see that if before 0 there's any output, this system is not causal because -2 is not 0, so it is not causal. Well, you can use counterexample here. Like you see -2, you can say h -2 is 0.8 to -2. This part is not 0, and n is -2. So here is u -2 plus 2, and this is 0.8 minus 2 times 1, and this is not 0, so it is not causal. And the second example, you see there is u minus t, because ut is like this and u minus t is like this. So it's like the left hand side is all non-zero. So obviously this system is not causal. So the third example is like, well, you have two parts. You have to make sure both of the parts are causal to make the whole system causal. I think we're going to just do this problem maybe later. Well, it is one problem from the homework.
One
Question.
Even just for the A example, can you just go over again? I understand the left shift by 2. Can you just go again how you determine that it's not causal? I see something it's not equal to 0, but I'm not sure how you arrived at that.
Okay, so let's start from the beginning. Okay. So it's like for causal, that means when there is no input, there should not be output. And for this is impulse response, that means the input is just non-zero at 0. That means before 0, there is no input. I just want to show before 0, there is no output to make a system causal. If there is any output before 0, that means the system is not causal. So you can use counterexample like saying when n equal to -2, it is before 0, h minus 2 is not 0. So there is input, but there is output before there is input, so it is not causal. Or you can use shift left by 2, saying, well, -2 and -1 are not 0, so before 0 they are output. So for the stable thing, well, we have already talked about BIBO stable, but here stable is a little bit different. This is when the system go to the far future, is it going to be bounded? So then the other way of saying that is when n go to the infinite, will hn be infinite? If hn is infinite, then it's not stable. Otherwise, it is stable. So for the first, let's do these examples. For the first one, we just want to find the limit from n to infinite hn. So this is 0.8 n u n plus 2. So this part, if n go to infinite, actually this whole part go to infinite, right? And ut on the right side is always 1, so this one at infinite is just 1. So I should not erase this. N minus 2. So this part is just 1, and 0.8, because it's less than 1, the absolute value of 0.8 is less than 1. So when n go to the infinite, this 0.8 to the n's power is just 0. So this one is 0. So it is bounded, so the system is stable. I have another example, but not here, but in the homework. It's like n times like which one? This first one? So this one is become smaller and smaller when n gets larger, right? When n gets to the infinite, this one is become 0. Okay. And this one, when on the actually on the whole right hand side is 1. So when n go to the infinite, this part is always 1. So the answer will be 0 times 1 is 0.
And that's enough without checking that if you put in a bounded input. So
well, 0 is bounded, so
so you don't have to do the
input. You don't have to do the input.
Okay.
Yeah. And there's another example. It's like n times like half to the power of n. Well, this one will go to infinite if n go to infinite, right? But this one will go to 0 when n go to the infinite. So, but because exponential is more dramatic than linear function, so the whole thing is actually going to 0. Question?
Can we take a ratio test to figure this out?
Ratio test? What is that?
It's used for infinite series and sequences to see if they converge or diverge.
Yeah, you can do that. Yeah. But most of the time it's pretty clear.
How do you determine which method you should use to determine stability? Meaning, when do we use this method?
Yeah, this method it can only be used for LTI system.
Okay.
And when impulse response is mentioned, it's like, well, this is the impulse response. By impulse response gives stability, then we use this method.
Okay.
But if you just give an expression well, use BIBO.
Okay, but if you plug in negative infinity for the first one, it's not.
Can I see?
For every single input.
Can I see that we don't care about that? It's like.
But if I were to give that answer on the test, like I wouldn't have done anything wrong, but the answer would be wrong.
Well, we'll put positive infinite. Yeah, it's like usually because this one is used in real system, it's like the system is going to explode or it's going to stay there. We're talking about the future, not the past.
Okay.
Yeah, so things like that we talk about and go to the infinite. Well, nothing. This is really a big thing for the convolution. So the first thing I just want to talk about is what on earth is convolution. Is that why we're talking about that? Because this answer is like the output of one LTI system is the convolution of the input system and its impulse response. So this is not often used because later on we're going to use Fourier series for that, Fourier convolution for that, Fourier transformation for that. But here, if we don't have any transformation thing, this is the answer. How you get the output from the impulse response, that's by convolution. But this is definitely not going to be on the test. What is going to be on the test is how you solve a convolution. Well, by my experience, there are at least going to be 3 kind of ways to solve that. First is using the properties of convolution. And the second is drawing graphs. And third one is by table. So the properties of the convolutions are, well, you have on homework 2, like study from page word to page word, and like commutative property, associative property, distributive property. Looks very familiar, right? If you just remove the star and make this just a dot product, everything works. But just to remember, convolution is not dot product, even though the math looks pretty similar. So, well, I think you can forget this page after this few minutes, but just to remember, convolution is not product, not multiply. And then we can still have the property of the delta function. It's like delta function, shifted delta function convolute with one signal is shifted signal. And this is the first type of problem we can solve is by properties. For example, in the quiz, you have something similar to this. You have one signal, pretty clear, and actually you can definitely draw it, something like this, from 0 to 4. And you want to find the convolution of this signal from several combinations of delta function. Nothing more, just the delta function. So this can be okay. Well, this will be first this shifted by -10. So here I have x itself shifted by -10, and minus, copy that minus here, and we have x n plus 10. And then you can plot that. Remember, this is just shift, no flip. So the areas, because this area is not symmetric, so you're not going to get symmetric answers. So, but in the quiz, I saw a lot of symmetric answers. Be careful about that. So the first range we'll get from -10 to -7, and then we have another range from 10 to 14. And this part, it goes up. Because there's minus sign here, this part goes down. And this is our answer. So I think this is the most easy problem for convolution. And then we have other kinds of problems, either continuous or discrete. for these two kinds of problems, there are two ways to do that. For both problems, you can draw graphs, like using graphs to detect the ranges and non-zero areas and so on. We're going to show that in examples. And if it is discrete signals, we can use a table to show the result of a convolution. So the steps of solve a convolution by drawing graphs. Sometimes we say it is 4 steps, but not very clear 4 steps. But you can remember things by these 4 words: flip, shift, multiply, and sum. And flip, shift, multiply, and sum. So I'm going to do that step by step. So let's first see the example. So the example, we do the convolution of 2 signals. One is a square wave, and the other one is the step function. So we can draw it. We can draw it like this 2, this from 0 to 4, and the other one is just from 0, and the magnitude is 1. Well, we know the shape of that. That's very important because we are drawing graphs. And the first step is to choose which one to stay and which one to move, because we know P convolution do the convolution with P, and H is the same as convolution H and P. So we choose one of them to stay and the other one to move. And usually, I think it's easier to choose the simple one to move and the complex one to stay. So what is simple and complex is when we see how many boundaries are there. So for the first signal, the non-zero, first a constant number, a 0 value, constant number, and 0 value. So we see 2 dramatic changes, like, or shall I say, there are 2 change of expression. So this is expressed by 0, this is expressed by a constant number. So there are 2 boundaries. But this one, there is on 1 boundary. So let's choose the step function to move and the other one to stay. So then we are going to draw functions. Remember, these functions are in the domain of tau. Like, well, the conclusion, the definition of conclusion, like h tau times x or p, like p t minus tau d tau. So this domain is actually that tau, something that is going to disappear in your answer. Disappear. So let's draw the one stays is from 0 to 4, magnitude 2. And the one moves. It's not the original signal. Actually, what we want to, this one is h. This one is h tau. Actually, what we want to draw is p t minus tau. So this one is flip and shift. So first a flip is time reverse, then we have a shift looks like this, and then we shift it by t, and so this value will be t. This t can be anywhere, even though I draw it here maybe near 0, but it can be anywhere. And based on the range of t, actually we will divide this convolution, or we will divide the range of tau into different ranges. So how to divide tau? It's like we are going to slide this moving one, like maybe from here to here to to here, to here, to here. And we're going to say, well, from here, I will divide one range, and from here to I will divide another range. By what? By when we see any boundary meet. This is a little bit abstract. I'm sorry about my language. So we see this is t, right? Let's move the t here. Let's move the signal here. And we see t touched this boundary 0. And then we will decide everything before that will be one range. And after this, we keep moving t to the right, here, here, and here. Then we see this t touched another boundary. Is this 4? So I'm going to decide from this 0 to this 4. This is another range. And after that, the t goes continues to the left, to the right, and then it is not going to touch any boundary. So everything after 4 is another boundary. It's another range. Sorry. So let's draw things like showing the boundaries. So first, we have the one that stays 0 to 4, and and this is t, and t is before 0, so the first range is t is less than 0. And inside each range, we want to find the common non-zero area. So this one is non-zero, this one is non-zero. We see they don't have overlap, so common non-zero area is empty. So the convolution is just a 0. And then this t goes inside 0 and 4. So we see there is another range t is less than 4, greater or equal to 0. And the common non-zero area is from here to here. So it is from 0 to t. So when we do the integral, when we do the convolution, before the convolution, the range should be non-negative, infinite to infinite. But here we know the only part that is not 0 is from 0 to t. And what's inside is ht times h tau times p t minus tau. But we know that these two functions are constant, so we just write the constants here. This 1 times 2 d tau. And this is going to be t times the amplitude. It's actually 1 square, so just calculate the area here. So it's 2t. And remember, this is the convolution. And the third range is like t goes beyond 4. Something like here, t 0, 4. So that is t is greater or equal to 4. And the non-zero area is here. And this one does not change, it's just the 0 to 4. So the convolution will be from 0 to 4, and times and inside is just the two constant, 1 times 2 d tau, and this is 8. So if we write the final answer, it's like ht convolution pt equal to 0, 2t, and 8, and the ranges are t less than 0, t between 0 and 4, so 4, and t greater than 4. And this is the final answer. Question? Okay. So yeah, sometimes you have 0 otherwise, but for that answer you already have the 0 area.
Can you go back to
The
the question?
question?
Oh,
This one.
the last problem. The big one. The last problem maybe.
This one is this one. I think.
How is it the result?
Okay. The result. Question.
40 greater than 4. T is greater than 4. What does it mean? T is greater than 4.
What do you mean by what the meaning?
Yeah, you see the range is from 0 to 4, right? T,
Oh, yeah. So t is greater than 4. That means that step function is something beyond 4, right? That means the non-zero area is from t to the left. And the non-zero area for the square wave is just from 0 to 4. And it's covered by the non-zero area of the step function. So the common non-zero area is from 0 to 4. Question?
You always say t where 0 was, but the function was.
Yes.
Right.
So, well, he made a very good point. It's like when we have an original signal looks whatever like this, maybe, and there was 1 0, and then we flip it and shift it, and when we flip it, maybe it looks like something here, and here is still 0 because flip is with respect to y-axis, and then shift that out. That will make this 0t. This is a shifted and flipped signal. Whenever so we make whatever at 0 to be at t. Okay, the last thing I want to do is try to do one conclusion by table. I think this is what Professor showed in the lectures. It is something similar to the by graph, but the only difference is like you don't divide ranges. What you want to do is you just want to find the common range. Well, let's see. You want to find the range of the whole answer. I will show you that in the graph, in the table. So the first signal is like from 1 to 3, and the value is n. So it should be like 0, 1, 2, 3, and looks like this one, and this one, and everyone else is 0. And second one is from -2 to 1, -1, -2. So it looks like this. So still, we can choose one to stay and one to move. well, similar because they both have two boundaries, but maybe this one to move because they are all ones. Well, it might be easier, but actually pretty same. So first we put the state, the one stays inside the table. Let's first make a table. Oh, sorry. And in this line is index, or yeah, or should I say just n? So we have -2, -1, 0, 1, 2, 3, 4, 5, and then let's put h tau here. Well, oh sorry, so not h tau, it's p tau here. P tau here is the triangle one, so it goes 1, 2, 3. This is the value of that, and everywhere else is 0, right? And then remember, what does h tau looks like? It's from -2 to 1, so h tau looks like this. But what we want is not h tau. What we want is hn minus tau. So still we're doing the flip, and it's with respect to 0, and it is here. And then make this one n, because it was 0. So what we are going to do is like we're going to search every n, search the value of the convolution from every n. Well, usually I suggest that you start from 0, go to the right, and when you find, well, it ends, then you come back to 0 and go to the left. So let's make a table like this. So this takes one space. So let's make n equal to 0 at first is actually like this one. So we see two overlaps. This one overlaps. There's two overlaps. So 1 multiplied by 1 plus 2 multiplied by 2, and you got 3. And this is the answer of convolution. And if n equal to 1, you shift this shape to the right by 1. So you got this. This is 3 overlaps. 1 multiplied by 1 plus 2 multiplied by 1 plus 3 multiplied by 1 plus 6. And 2, 1. We still got 3 overlaps, so 6. So I'll circle the overlaps. And 3. Keep shipping. This one is 5. And 4. This one overlaps, is 3 times 1, and this is just a 3. 5. You should keep going until you see this kind of situation. 1, 1, 1. There's no overlap anymore, and even if you keep shift to the right, you are not going to see any overlaps anymore. This shows you a sign that you can stop here. Then we go back to 0 and go to the other side, like -1. So and this one overlaps and gives you 1, and -2. Nothing overlaps. And if you keep shift to the left, still you won't see any overlap anymore, so that shows you can stop here. It's like when you can only stop when you have these zeros on both ends. So any question about this table part?
How do you get this number?
Which numbers? On the right.
On the right.
So this signals. So these are the index, right? This signals is p tau, and these signals are hn minus tau, and I see which part are overlapped. You see the overlap vertically, and multiply them each by each, and sum up all the products to get one number here. And these numbers are the convolutions. These numbers are the index.
Is there like a sign?
Anyone have a blank sheet? Sorry for that. Question?
Can you draw the final graph?
Well, okay. If I draw the final graph, I see it goes from -1 to 5. So let's say.
Yep.
-1 is 1, and 0 is 3, 2 is 1 is 6, 2 is 6, 3 is 5. 4 is
So see you next week.
yeah. See you next week.